In the previous video, we discussed that in the worst case, our tree's height is directly proportional to n, which is h is directly proportional to n. So in order to improve this worst case scenario, what we want to do is we want to transform the spindly tree into a bushy tree, which looks something like this, using some tools and algorithms. And the first tool we are going to discuss is the tool of rotation. So basically, we can transform this tree, the spindly tree, into this more bushy tree by rearranging or reorienting the tree without affecting its semantics. And what I mean by semantics is we have this BST, right, which has this property everything on the left is less than everything on the right. So in this case, you can see that 51 is greater than 25, 65 is greater than 51, 85 is greater than 65, and 91 is greater than 85. So it's a perfectly valid BST. Now, this BST property should remain the same after we perform some operation on the tree. So in this case, when we rotate the tree in this order, which is we are basically rotating it anti-clockwise, in that case 65 will become the new root and 51 and 25 goes down, which is we have this new tree that looks like this. But you can see that this new tree also satisfies the BST property, which is 51 is less than 65 and 21 is less than both 65 and 51. Similarly, 85 is greater than 65 and 91 is greater than 85 and 65. So the key here is the semantics, which is we do not want to change the semantics. We want the tree to remain the same, the meaning to remain the same, but we want to reorient the tree. So in the last video, when we talked about like the ways to insert n elements, we discussed that there are n factorial ways. Now we are going to see that actually there are only Catalan n number of different BSTs that are possible out of this n factorial number of ways. And what I mean by this Catalan n, it's basically a numbers, series of numbers, just like we have Fibonacci numbers. Catalan numbers is basically a function where if you input n, it will return how many possible states are possible. It's a combinometric tool, and we are not going to go into depth for this. But what I want you to get out of all this is that, like, let's say if we had n equal to 3, we had 6 different ways of inserting it, which is 1, 2, 3, 1, 3, 2, 3, 1, 2, 2, 3, 1, 2, 1, 3, and 3, 2, 1. Now I have drawn every particular state, which is you have 1, 2, 3 will look like this, 1, 3, 2 will look like this, 3, 1, 2 will look like this, 2, 1, 3 will look like this, and then 3, 2, 1 will look like this. So out of all these different trees, you can see like this one is more splendidly, this one is more splendidly, again this one is splendidly, this one is splendidly, but only we have one bushy state. So our goal is to transform all these different spindly states into a bushy state. So we have these 4 different states and we want to transform them into this state, or we want to reach this state. And I'm going to make a claim that, let's say if like whenever we are creating a tree that has, let's say, 100 nodes, we can apply these tools of rotations to every 3 elements. Like whenever we have 3 elements that are inserted into a tree, you can make sure that any, like, we'll have one of these 4 states, right? So you have to make sure you transform that into uh, this goal state after every 3 nodes, which is, let's say if you have these 3 elements, so after you insert these 3, you'll have a tree that looks like this. Next, when we are going to insert one more, we'll again transform another set of 3 nodes to look like this. So basically what I want to state here is we will always work on 3 nodes, and that's the gist of rotations, which is these tools of rotations are always used on a set of 3 nodes, and then we are going to apply these rotations again and again recursively throughout the entire tree, which we are going to see very soon. So there are four different cases of rotations. The first one is left rotation, which is the right case. So let's say if we try to insert the numbers 1, 2, 3, our tree would look something like this, which is 1. And then when we try to insert 2, it will go towards the right side. Then when we insert 3, it will go towards the right of 2. So if you want to transform this 1, 2, 3 into the goal state, our first tool, like first type of tool of rotation, is this left rotation, which is we are going to rotate it anti-clockwise. And we are going to rotate it always at the parent node, which is we have these three nodes. So 2 will become the parent, 1 will become the left child, and 3 will become the right child. So this is an example of single rotation because we have just rotated it once. So the key here is if we have a right case, which is 2 is on the right of parent and 3 is on the right of the child. So basically we have this right case, and in this case we left rotate to reach our goal state. The next case is going to be pretty symmetrical, but instead of this one we have something like this. But before we go to this case, this is a pseudocode of how we can transform like these three nodes. Now, one thing I want to state is like whenever we are performing like rotations, there can be more elements attached to it, which is this 3 can have some subtrees which we do not know, 2 can have another subtree, and 1 can have another subtree. There cannot be more than these subtrees because it's a binary tree. So if you want to write pseudocode for this rotate left case, we are going to pass this node, which is called n, like or node. So this tree we are going to pass into this function. Now I'm calling these subtrees by name, which is A, B, C, and D. So not only are we transforming this to 2, 1, 3, but we are also changing the order of subtrees, which is C will remain attached to this 3, D will remain attached to this 3 as it was in this figure. A will remain attached as left subchild of A of 1. Now 2 has become the new root node. So it has one child, but now since it is the root node, it already has two children, which is 1 and 3. But we know that this B subtree, which is attached to the left of 2, this is less than, like B is basically less than 2 because of the BST property, which is all elements on the left of 2, is less than the root node. Also, we know that B is greater than 1 because it's on the right of 1. So basically we can reorient B to be attached to the right child of 1 in this case. And our tree would look something like this. So I'm not going to attach all these subtrees, but for all the future rotations that we are going to discuss. But basically the key idea is that if you rotate left or right, there might be one subtree that needs to be attached from one index to another based on some reorientation. But still we have the same order, which is B is, now the B is greater than 1 because it's the right child, and B is less than 2 because it's on the left. So semantically the trees look the same. So I'm now going to cover the pseudocode bit by bit, which is in this case, first we define grandchild, which is nodes right left, which is node is 1. So nodes right is 2 and left is B. Okay. So at the end of our tree, it should look something like this. Next, we are going to define new parent. So new parent is equal to nodes right. So node is 1, nodes right is this particular subtree, which is new parent will point to 2, that has all these extensions, which is B, and then 3 has C and D. Next, in the next statement, we have something like new parents left is equal to node, which is new parents left, which is in this case, this B, we are going to change that to point to the node element, which is node is still pointing to our tree. So new parent now becomes 2, 3, 1, C, and D. And now 1 is actually having a subtree like A. This also has 2, 3, B, and then C and D. Next, in the next statement, we make nodes right, which is this nodes right as grandchild, which is now this was pointing to the node, right? So we want to make nodes right child, which is this entire subtree, pointing to the grandchild, which is in this case B. And that's how we achieved like our entire tree, which is in this case, our tree is something like this. And new parent is still pointing to 2. So we are going to return this entire tree, which exactly looks like this. So basically, whenever we are trying to rotate left, the gist of it is that we are just manipulating some pointers. We are not doing anything else. And it takes like constant amount of time to manipulate some pointers. Like you can, there are stepping exercises this week on like how to rotate a tree. So make sure you complete all the rotations, which is rotate left. And we are going to discuss the other 4 very soon. The next case is the right rotation, which is if you have the left case, which is you have this node, we have another node which is on the left of this, and another node which is on the left of this. So in this case, we right rotate at 3 or rotate clockwise. So in this case, we get like 2, 1, 3, which is our goal state in just one rotation. So it's a single rotation case. The third one is the right left rotation case, which is in this case, it's the right left case, which is you have this right, the child is on the right, and the grandchild is on the child's left. So it's like right, left. And in this case, we cannot solve this using just one rotation. So we have like 2 different rotations, which is first we rotate right at this number 3, which is the child node. And right is like clockwise. So after that rotation, our tree would look like something like this, which is 1, 2, 3. Next, we rotate left at 1, which is now we rotate left. So this is an example of double rotation because we are rotating it twice to reach to our goal state. The last one is left-right rotation, which is we have this left and then right. And in this case, you are going to do the completely opposite of what we discussed in the last slide, which is you first rotate left on the bottom case, because this is like, again, this is right, so it's like left rotation to achieve this state, because 3 will have now 2 on its left and then 1 on its right. Next, we are going to right rotate at 3, which is, in this case, we reach the goal state. So all these different forms of rotations will take constant amount of time, and you can build these left-right and right-left rotations by just calling the functions on right and left rotations. You do not need to do anything else. If you pass the correct pointers, it will always work. So fundamentally, there are just 2 rotations, which is left rotation and right rotation. Now, the issue with this tool, the rotation, is that it can get very messy on a pre-built tree, which is like, let's say if I give you this entire tree, which is a BST, and I ask you to convert this into AVL, this can get really messy because you are like performing some rotation at a position X, like this might have some subtrees and it's like unbalanced. So what happens is, like all these rotations or the tools that we are going to use, we are going to apply some algorithms to it, which is we are not going to apply this to a pre-built binary tree, but we are going to use a preemptive approach, which is whenever we insert some elements, then we perform some rotations. And for those preemptive measures, we have like different algorithms. The first one that we are going to discuss is AVL, and in next set of videos we are going to discuss red black trees. Those are the two most common ones. And in the next video we'll start with our first algorithm, which is for the AVL trees, which is how we can like use these rotations as tools in some certain algorithms to make sure we do not have to deal with the messiness of changing a BST to a AVL tree. So the core thing I want you to take away is you'll never be asked something like you have this BST converted into AVL. You'll always build a AVL tree from scratch rather than converting an unbalanced tree to a balanced tree, because it gets like really messy.